All right, Ilić, thank you for being here today. You are one of the few people, I guess, that have written a book on IPv6, which by default, I guess, makes you an expert. And
well, the thing is, you're not an expert before you start writing, but after you write a book, you must be an expert. Otherwise, the book sucks, right?
This is how it works. So you start as a novice, and then when the book is done, you're an expert.
Yeah.
I should write more books. All right. So thank you very much for being here today and telling our students a little bit about IPv6.
My pleasure. You want me to start right now?
Sure.
Okay. So you asked me to say a few words about my background. These are the topics for today. It's only a few. So basically, I was in college in the early 1990s, and then I basically ended up in the Dutch internet service provider business that was starting up. So we had dial-up modems, and a few years later we got ISDN, all that kind of good stuff. Then in 2000, I decided to make my own one-person business and help ISPs with their network configurations. And then I wrote this book about BGP, the routing protocol, in 2002, and a few years later, the IPv6 book. And then in 2007, I did a master's and I started work on a PhD in Spain. And then I got involved with the Trilogy project where I met your esteemed professor. I also did a lot of IETF work in those days, ended up as a co-author on 7 RFCs, and I was a writer for a bit less academic stuff for Ars Technica, a big tech website for about 10 years, and then until recently I did some work for the Dutch government, but now I'm back to my one-person business again. And all this time, IPv6 has been going on because look at this. First RFC, first IPv6 proposed standard, December 1995. So the internet has been around for 51 years now, and for half of the time we've had IPv6. So that's amazing. So why do we need IPv6? Well, it's very easy. In 1991, they created the first version of IP, which we call, of course, IPv4, because why start with 1 or 0? Just start with 4. And it has 32-bit addresses. So you can't use every single one of them. So there's about 3.7 billion usable ones. And at that time, there were already that number of people on the planet, and they didn't even have cell phones then. But it started becoming clear that this wouldn't work. 32-bit addresses for a network that spans the entire world. So we need to make more addresses. So then you need more bits for the addresses, and if you have more bits, you need bigger packet headers, and if you change the packet header, then you have to use a new version number to show that you are doing something different. So people are not going to get, or machines are not going to get confused. So number 5 was used for some other protocol that was the IP. So the next free version number was 6. So there we got IPv6. This is the header that is put in front of every IPv4 packet. And then, of course, there's an IPv6 header. As you can see, it is about twice as big. So the IPv4 header, it is optimized for 32 bits. So it's 5 32-bit words. The IPv6 header is optimized for 64 bits. So it's one 64-bit word and then 228-bit addresses. And it looks fairly different. So there are 3 fields that are named the same. Of course, the addresses are much bigger. That was the whole point. And then all the other fields, they look different, but actually the blue ones are just identical to the ones for IPv4. They're just named slightly differently. The purple ones in IPv4, we threw them out, don't need them anymore. And there's the payload length. which is slightly different from the total length in IPv4. So in IPv4, we count how big the entire packet, including the header, is. With IPv6, we only put the length of the payload in the payload length. So the length of the header itself, 40 bytes, is not included in this. So we have these cool new super long addresses, 128 bits. I mean, it's like, in Holland, we had phone numbers that were 9 digits. They decided it's not enough, so they made it 10 digits. But that would basically be like we use 36-digit phone numbers. I mean, 9 is not enough, just quadruple it. They really went overboard in the other direction after having not used enough bits in the 80s with only 32. So where do you get these addresses? Well, first of all, you just make one when you start up. So just when you connect to a network, even if you are the first one there, so you have nothing to talk to, no routers, nothing, no configuration. You just create an address out of nothing on all your IPv6 capable interfaces. This is called a link local address. IPv4 has something slightly like that, and that is the 169.254 addresses. But it only uses that as long as it doesn't have a real IPv4 address. While with IPv6, it always uses link local addresses, even if it later gets one or more real, regular global unicast addresses. Okay, addresses for network protocols, for layer 3 protocols, they have a hierarchy. I mean, it's not like an Ethernet address, a MAC address, where you just have a bunch of bits and you have no idea where one address is in the world. I mean, we can't keep track of all the Ethernet addresses in the entire world because the routers would have used too much memory for that. So there is a hierarchy, a network part that is shared by everybody connected to the same local network, and a host part that is that identifies the device within a local network. So this is how things used to work in the 1980s and 1990s. We didn't just have IP, we had a bunch of different protocols, and they all solved this in different ways. So for instance, the IPX protocol had 80-bit addresses, 32 for the network part, and 48 for the host part. AppleTalk is basically the same idea, except that it's much smaller. So only 24 total bits, 16 network, 8 host. These were never intended to be global networks, by the way. These were LAN protocols for local area networks. And then the people that gave us the OC model, they also had their own protocol, the connectionless network protocol, CLNP, and that had variable addresses that were maximum 160 bits. Actually, they always used the maximum, so I mean, why not? But of course, because it's variable, that means the two parts are also variable, but they basically always put the MAC address in the host part, so that was always 48 bits. So what does that leave for the network parts? That would be 112, I think. Yeah.
Illich,
yeah.
Do you know if CLNP was ever actually built? Could you buy a device that spoke it?
Yes. So the thing is that basically in the 90s there was this effort that was called GOSSIP, G-O-S-I-P, and there was a mandate, I think, from the American government. You don't want all this different stuff. You don't want to run multi-protocol routers with multiple routing protocols and different addresses. That's a big mess. So we want to standardize, and obviously we go to the international standards. So we want to standardize in CLNP. So people like Cisco, they just built it in all their routers. And then we forgot about this because everybody started using IP. So it was there. And actually, I remember in 1999, when I was working for UUNet, or Verizon Business is called now, and we had a really big network, and we had a design from America, and we used the ISIS routing protocol. And that's actually a routing protocol from CLNP. So that means you also have to have a CLNP address in order to run the protocol. So in the really big networks, they prefer ISIS as an internal routing protocol over OSPF. So that means they have to run ISIS. So at that point I said, well, there's probably more people running ISIS than there are people running IPv6. That's no longer true.
The reason why I'm asking is it must be very difficult to produce high performance router equipment, so the forwarding part, with a variable length address.
Well, I've always said that basically the mistake they made with IPv6 is they made the addresses fixed length, because 128 bits is usually much more than you need. But if you do weird stuff, it's not enough. So basically, like in the army, they have two size helmets, too big and too small, right? Now, variable sized helmets are probably hard. I don't know. But so I was always arguing, well, if it starts at the same place, then you can basically do a prefix match, right? And you don't care about what comes after your prefix. So I think they could have done it. It would be a bit harder, but I don't think it would be a showstopper. Of course, everything that comes after the first address, the destination address, in this case, then that would be at the variable place. So that would be harder. So for firewalls, I think it would be harder, but just for pure forwarding, I don't think it should make a big difference.
Oh, that might be true, yeah. And IPX,
yeah.
And IPX was from IBM, wasn't it?
What was from IBM?
IPX, SPX, wasn't that IBM?
I don't know, but I mean, I don't remember who came up with it, but I do know the guys who made it really popular was Novell, with Novell
Yes.
Network. So they used IPX.
Right.
Where was I? Okay, yeah, the CLMP. The thing is, I don't think it was ever implemented in ASICs like IP was, because back in the 1990s when they had this gossip and it was implemented fairly widely, then the routers always still use software, so they were very slow. And of course, in software, it doesn't make as much of a difference. Okay, so how does it work in IP? In IPv4, originally, we had 3 options for how big the network part and consequently the host part are. So 8-bit network, 24 hosts, 16 for each, or 24-bit network, 8-bit host. But then later on, they decided this is wasteful and inflexible. So we make the boundary between the network part and the host part, we make that variable. So this is called CIDR, classless interdomain routing, and VLSM, variable length subnetting. Sorry, I didn't put that in the slides, so you'll have to do this by ear if you want to look it up. So this is how you get your IPX address. You have your MAC address, your Ethernet address. Then the IPX router broadcasts the network part, 32 bits. Just take the 32 bits from the router, glue your own MAC address bits at the end, you have your 80-bit address. Now, when you need to do the address resolution protocol in order to find the MAC address, so you can send a packet over the local network, the ARP for IPX is fairly simple. Just remove the network part again, and you're done, right? AppleTalk. So basically, same idea, except that the host part is really small. So we don't have 8-bit MAC addresses. So you just generate a random number and then see if that's already used. And if not, you generate a new one until you have an unused address. And of course, they have to use a regular ARP. I didn't look up how that works, but I assume it's fairly similar to IPv4 ARP. So CLMP, I think there's actually the equal sign is incorrect here because they do put in the MAC address, but I think it's not a rule. So you probably have to do some kind of ARP. They of course use a strange word for something like that because they cannot use regular links or anything. For instance, they don't use the word address. They call it network service attachment point, NSAP. So just like you walk into another dimension where everything is slightly different, but even if it's fairly similar, it's named completely different. So IPv4, basically you can get your address with manual configuration. And remember, DHCP is only a couple of years older than IPv6. So for 20 years, there was only manual configuration with IPv4. So you get it manually or from DHCP, and then you use ARP to find the MAC address. Now, so we have some options how you can do this. This is, by the way, I understand you already know ARP. Basically, IPv6 uses the same idea, but they call it neighbor discovery, and has a whole bunch more options and extra fields and all kinds of stuff, but the basic function is the same. So how does IPv6 do this? Well, basically, it lets you do all of these. So you can have DHCP v6, so like IPv4, but then the IPv6 version. You can have, of course, manual configuration. You can take bits from the router, add your MAC address, take bits from the router, add a random number, or even take bits from the router and add a cryptographic signature. So you can actually claim ownership of an address with the crypto hash. So a whole bunch of options. But the most basic one is the stateless auto configuration. Stateless means that there is no DHCP server or something like that that has to remember which address went to which device. Because if you have a lot of devices, you have to keep a long list. The DHCP server reboots, then the list is gone and complexity. So we start with our MAC address, but that is only 48 bits. And 64 bits is such a nice round number, so we make it 64 bits by putting a few extra bits in the middle. Then we flip the global local bit. Don't remember the G or the L comes first. So that's a bit in the MAC address that tells you if the MAC address was given out by the owners of the MAC address space, so you know it's unique, or that you came up with it yourself, so you know that it may not be unique and someone else may have it. We flip this bit. Now I have a modified extended unique identifier 64. Then we take the bits from the router, also 64 bits. We put the whole thing together, and we have a nice long 128-bit IPv6 address.
Do you know why they put the extra bits in the middle? Was there a particular reason?
No, I don't. I do know that the idea was that in the future MAC address would be 64 bits. For instance, FireWire uses 64-bit MAC addresses, but then that didn't really end up happening. And the interesting thing is on a Mac computer, so other type of Mac, the FireWire addresses also have the FFFE in the middle. So basically, they use the same procedure to get a 48-bit address and then add the extra bits, because they need a 64 bits there as well.
And what is the reason to pretend it was a local MAC? Because if you start out with a globally assigned MAC from IEEE, you would flip the bit indicating that it's now local only. What is the reason?
Well, no, the reason to flip it is that if you configure something manually, then you're probably not gonna put 1 in the place of the global local bit, because it would have to be a 1. So if you then if you put the 0 there, which is easier because you just type a whole bunch of zeros and then 1 at the end, 2 for the next one, then that would indicate that these are addresses derived from global MAC addresses. So by flipping the bits, that means if you keep it 0, that means it is not global. So they really thought of lots of stuff right back in 1995. So now there is a slight issue. Even they thought about privacy, about how bad we would be tracked by Facebook and Google and everything 20 years later. So suppose that I take my laptop or some other device here at home and I connect it to the network. and there's in this lower 64 bits is my MAC address. And then, so Google sees the MAC address. I take my laptop, go to university, and open it up, and a completely different address, because it's a completely different place, completely different network. But the MAC address bits are the same. So they can follow me around wherever I go, even if I disable all my cookies and other tracking. So the privacy people really didn't like that. So then they came up with this whole idea of putting a random number in the lower 64 bits, so that if I connect to another network, it generates a new random number. And then you cannot track people by their IPv6 address anymore. So this became the default between 2005 and 2010 or something. So basically everything that does stateless auto configuration does this these days.
So you could say that it was good that the uptake of IPv6 at that point wasn't that high.
You mean our privacy crisis would have come earlier if everybody had been on IPv6?
Who knows?
Yeah. Okay. Now there is, of course, an issue. Actually, it can happen that they don't really burn the proper MAC addresses in the card. So you buy a 5-pack, all 5 have the same address. That's pretty annoying. And of course, if you generate the addresses randomly, then you have the birthday paradox. I think you have the number of bits, so 2 to the power of 32, 1 in 4 billion chance that you generate two of the same ones. So that is, of course, completely unacceptable, that something bad happens once every 4 billion times. So actually what the systems do when they select an address with stateless auto configuration, they first check to see if someone else is doing it, just like with AppleTalk. AppleTalk, of course, only had very short 8 bits for the local part, so it had collisions very easily. The only thing is that if it does detect a collision, then it basically doesn't know what to do. So then you don't have IPv6 that day. So that's not so good. But at least you are not using the same address as someone else. Okay. Now, so there's a whole life cycle of these addresses. So what you can see is that you start with just your link local address. Then you get a router advertisement. You create a new address that's called tentative. You can actually, if you have a Unix system, you type ifconfig, you can actually see that, it shows that. Then you do duplicate address detection. And if it fails, then you have duplicate. If it's successful, so nobody says, hey, that's my address, then the address becomes valid. And then there are some timers. Actually, there's 3 timers, one for the router advertisement itself, one for the preferred lifetime for the addresses. So that then means it's a good address. You prefer to use that. And at some point, it's getting a bit stale. Of course, if you keep getting the router advertisements, then you refresh the timer. But if the router advertisements stop, that doesn't mean the address goes away immediately, but after some time, then the preferred lifetime expires, and you say, okay, it's no longer preferred, but it's still valid. And then there's a second timer, the valid lifetime. If that also expires, while you are in deprecated, so the preferred is expired, but the valid is still not expired, then you can still use the address for stuff that is already happening, so you can continue your sessions. You just don't like to use that address for new stuff. So if you have other addresses, you use the preferred other addresses for that. When the valid lifetime expires, the address becomes invalid, and after some time it's removed from the system. So this is how we write down IPv4 addresses at first. So we take the 32 bits, split that in 4 8-bit segments, translate those to decimal, put periods between them. I think you all know how that works. With IPv6, slightly different. So we take 8 16-bit groups, and we write those down as 4 hexadecimal digits. Well, up to 4, of course. If there's lots of zeros, then you don't need to use all the hexadecimal digits. And then we put colons between them. So that's how you get those long, complex-looking IPv6 addresses. Now, fortunately, we can often shorten them a bit. We can compress the zeros. So basically, anytime there is multiple zeros in an address between 2 colons, then you can leave out a sequence of 0 colon. So look at the slide and you can see how it works. The thing is, of course, you can only do that once, because if you do it in 2 different places, then how do you know how many zeros you removed from one and how many from the other? And it's pretty radical. So if you have the unspecified address, which is all zeros, you throw them all out, you just have colon. That means 128 bits, 128 0 bits. So with IPv6, there are explicitly different types of addresses. We already talked about the link local addresses. Then, of course, there are the normal addresses you use for one-to-one communication over the internet. Those are global unicast, well, global, of course, because you can use them all over the world, and unicast from one-to-one. Site local unicast, that is basically like 10 addresses, like the RFC 1597 addresses. So you can use this locally, but not out on the internet. There's basically a whole bunch of stuff going on with the regular site local addresses, where everybody uses the same site local addresses. So they eventually decided, well, even for the site local addresses, we want people to use unique address ranges. So we now have unique site local addresses, or ULAs, to avoid some issues with overlapping address ranges. Multicast, one sender, many receivers, or basically a group of people all interested in the same stuff, and the members of the group can all use the same address. Anycast is from one to a group, but not to all the members of the group, but to one member of the group, but you don't know which one. So for instance, that is useful with DNS. All the DNS servers are going to give you the same answer for a request. So you just send to the Anycast address, it's delivered to the closest DNS server that's a member of the Anycast group, and that one gives you the answer. This is a little cheat sheet that shows you how the different address ranges find their place in the IPv6 address space, including some address ranges for different kinds of tunneling. We'll talk about tunneling a bit later, but it's basically not really used anymore. So one thing is that if we have all these options to configure our addresses, then we need to choose the best one. And anytime you get to choose, that is good, but it's also bad, because now you have an opportunity to choose the incorrect, to make the incorrect choice. So that sucks. So router advertisements, we already talked about those. They are sent out by the routers, and that the most important function of the router advertisement is that you now know there is a router, and I can send my packets to this router, and the router will forward them to other parts of the network, other parts of the world. So it gives you a default gateway. Then we have the 64-bit the first parts of address blocks, so you can do stateless auto configuration. Then, of course, the addresses have to be in the router advertisements. That's not always the case. They can be left out. And also there is a little flag, the autonomous address configuration flag, which has to be set to 1. Otherwise, you cannot use these address prefixes for stateless auto configuration. There can be addresses of DNS servers in there, but that is an option that was defined later. So it's not 100% supported. And these timers that I talked about, we don't have broadcast in IPv6, so all this stuff is multicast. So that is fairly efficient in Ethernet. On Wi-Fi, it is a bit of a problem, but basically the same as broadcasts. The interesting thing about multicasts is that only IPv6 systems listen to the addresses of IPv6 multicasts. So with IPv4 ARP, for instance, they use the broadcast address. So all systems get these broadcasts even if they don't run IPv4. So this is much more efficient. Okay, so there's two other flags that define how the hosts configure their addresses, because the router advertisements tell the hosts what kind of address configuration is in use here. And there is the mbit, the managed config flag, that tells the hosts, okay, use a stateful protocol to configure your address. So we know stateless autoconfig, so not that, because it's stateless. We want stateful, which means DHCP, which keeps the list of who got which address, which people in enterprise networks love, because they can then see if something bad happens, hey, this person had that address at that time. And then we have the other stateful config bit that says, well, talk to the DHCP server, but ask for other stuff. So if the mbit is 0, so you don't get an address from the DHCP server, you can still get other stuff from the DHCP server, for instance, your DNS addresses or your search domains, that kind of stuff. So DHCP6, like I said, the basic idea is that it is like IPv4 DHCP, but it's basically a completely new implementation. So it's the same idea, but a new implementation for IPv6. And it doesn't provide all the stuff that IPv4 DHCP provides, because a lot of stuff is already in router advertisements. So you cannot run DHCP6 if you don't get router advertisements. Already talked about the M and the O bits. There's also an option in DHCP6, and that is prefix delegation. So you get a prefix, and that is different from the prefix you get with stateless autoconfig, because this is the prefix you can use for a larger network. So I get from my ISP a /56 prefix. My devices in my house use 64 bits for the host part. So they need 64 bits for the network part, which is standard. But I get only 56 bits. So I have 8 missing bits. And these bits I can fill in myself to number my subnets in my house. And actually what I can do is I have a guest network. So I have one subnet for my regular network, and I have another subnet for my guest network. So basically I could, if I had a really big house, I could have a separate guest network in each room, and I could have a huge mansion with 250 rooms and still have enough subnets to fill that with just a home IPv6 connection to my ISP. And on IPv4, they only give you one single IPv4 address. And even that, then you're pretty lucky these days, because that's not happening everywhere anymore. Okay, so that's prefix delegation.
One question. So you have obviously configure these things at ISPs. So how many people really get a /65 at home when their ISP is giving them
/56?
Is it always?
So basically, there was this rule that said, how do you decide how many addresses you give to a user? So then you ask the user this question: are you sure you only need one address? The user says, yeah, I never need more than one address. You give them one address. If they say, I don't know, maybe I need more. Then the next question is, you ask, are you sure you never need more than /64, so one subnet? And if the user says, well, I mean, one subnet is enough for all the Ethernet cards ever made in the history of Ethernet, so that's enough. Then you give them a /64. And if they still say no, then you just give them a /48. So that's enough for 16 bits for subnets, so 65,000 subnets. And that's if they say they need more than one subnet, then you just give them a /48. But then some people did some calculations and said, well, if we are being really wasteful and really unlucky and we grow really fast, all these things, then we might, if it's really bad, run out of address space if we just give everybody /48s. So that rule basically is it's not like it's completely wiped out. So if as an ISP you want to give your users /48s, that's okay. But most of them said, well, yeah, and who needs /48? That is too much. So I think basically what can happen is /64. They think one subnet is enough. And that is not good, because then basically you cannot subdivide in your own house, for instance, the guest network thing that I was talking about. So that sucks. Then you have /56. So that's nicely between 64 and 48. So that's fairly common, I think. Or maybe you can do /60. So 16 subnets, and I think that's enough for home users. And the thing is, if you, for instance, if you're a school, you get a /56. Then when you assign your 200th subnet and you think, okay, I need a bit more than 250, then you already have 200 in use. So what I would say is just give people /60, because it's enough for simple use. And if that is not enough, then maybe 56 is also not enough. So let them hit the ceiling early and then give them a /48. So that has always been my position, but I think /56 is fairly common these days. But ISPs can do this any way they want, so you never know. And actually, what's really cool is you can also then have my cable modem gets the /56. But what if I have another IPv6 router behind the cable modem? Then, well, the cable modem can then say, okay, I have enough bits. Then I give some other bits to the next router. So if I turn on my Apple Airport Extreme base station, and remember, they were discontinued around 2015. So there's a 7-year-old code that's running there. They actually get the /60 from the cable modem, and they create their own regular network and guest network. So I have 2 regular networks, 2 guest networks, and it's all automatic with all real global unicast addresses, no NAT, and the firewalling is up to the device. So some are strict and some don't do any firewalling. So that is another thing to watch out for with IPv6. Okay, so basically with so many choices, there are very many that will not give you what you want. So basically 2 blue ones. Then you get, the black ones, you get the 3 black ones, you get working IPv6. The red ones are probably not good. And then the other colors, they might work, but are not ideal. But this was 10 years ago, and we're just figuring this out, not in the sense of the standards, because those were okay, but how do you apply the standards, how do you combine stuff? So the same with ISDN. I remember in 1995 or something, then we got ISDN, a digital phone line. And there were all these different protocols to run your IP over ISDN. And for a year, it was a mess. And then everyone decided, okay, we do it this way. And then basically all the issues went away. So these days, basically, unless you have an Android phone, and in some situations it doesn't work because it doesn't support DHCP-v6. But all the other stuff just supports everything. And the routers are smart enough to only send out router advertisements that make sense.
Did you say Android does not support DHCP-v6?
Right.
Huh.
There's this one guy from Android who shows up at IETF meetings and he doesn't like it. He wasn't the only one, because there were huge discussions between the people who like DHCP-v6 and who didn't like it. But eventually we decided, well, basically we have to live together. So everybody supports DHCP-v6 even though we now have a DNS option in the router advertisements, because this was the sticking point. You need DNS addresses. You couldn't do that with stateless autoconfig for a long time. But the Google guy, he held out, so no DHCP-v6 in Android.
That's interesting.
Yeah, like I said. So now we know about IPv6, what it can do, but how do we get from the situation where nobody has IPv6 to the situation where everybody has IPv6? We don't have to worry about all these IPv4 addresses anymore. Oh, by the way, I was reviewing my slides this morning, and I was planning on putting in one that shows when we ran out of IPv4 addresses, but I forgot. So basically, we started actually running out, where people who were ISPs who needed IPv4 addresses to give to their customers, they were told, no, we don't have any anymore. It started in 2011, and then last year, early this year, so it started in Asia, where they were going through them very fast. Then it went to Europe, North America, Latin America, and this year in Africa, they also ran out because they didn't go through them very fast. So there's no place in the world anymore where you can just ask for IPv4 addresses and get them the way we always used to in the 90s and early 2000s. So for all intents and purposes, we're out of IPv4 addresses. Fortunately, you can reuse them. It's not like oil, where you burn it and then it's gone. So we don't have easy access to more IPv4 addresses anymore. So we really need IPv6, but that's still, it's hard to move from IP4 to IP6. So why is that so hard? I mean, here in my house, I started with 10 megabits Ethernet, went to 100, 1,000, and now 10,000 megabits. And the rest of the internet didn't care. I didn't have to send out any emails, please upgrade your communications to me because now I have faster network. So that was easy. For instance, the DNS, it can run over UDP like normal, but it actually just switches to TCP if the packets get too big. No problem at all. Twitter, I mean, if you want to connect to them without security, you just use HTTP ://twitter.com. And then if you want to use encryption, just add the S. We now run over different TCP ports and do all kinds of extra stuff. Nobody cares, it just happens. So why is from one IP version to another so hard? Well, the thing is that the lower layer stuff, the Ethernet and the Wi-Fi, that is local. It's in my house. My ISP in the street upgrades their network. I don't care. I mean, it gets faster, but it doesn't work differently. If on the other end of the network, the world, they upgrade something, it's all local. The applications are end-to-end, so the middle doesn't care. Just packets, and what's in there, they shouldn't concern themselves with it. So that's two ends that need to upgrade. But the IP, the Internet Protocol, the application needs to support it. The host software, the operating system needs to support it. The local network, the router, the next network, the next router, all the way to the other side. So everybody in the path has to support it. That makes it so hard, and that makes it so slow to upgrade. So actually, we've done this before, because in computing, and therefore in networking, nothing is ever new. I mean, all the great ideas are from the 60s. We just had to wait until the computer was fast enough to run the algorithms. So actually, in the original ARPANET, original internet, used a protocol called NCP, Network Control Protocol, but then that did everything, and that was not good. So they moved over to TCP/IP, IPv4. They designed this. They published this in 1981, and then they took 1982 to move over, to transition. So how long did it take? Well, the entire year. But that was only because at the end of the year, they just pulled the plug on the old network. So the last ones that hadn't done anything the whole year, they had to move over. I think that sounds a bit like the Brexit, I think. Okay, never mind. So it took a year. They didn't quite make it in a year. even though there were only 100 big mini computers and mainframes connected to the entire internet, they only ran 3 protocols: mail, telnet, FTP. That was all. So these days we have billions of devices. We have hundreds or thousands of applications, different applications, let alone different implementations of the same application. Everything needs to be changed. So this is going to take forever. Well, I mean, we could be optimistic and say you just take one day. For instance, how about you, Rolf? Do you think next Thursday we could do the change? On Wednesday we turn off IPv4, and on Thursday morning we turn on IPv6. So we just agree the dates with all the internet users, and we're done in one day. So obviously that doesn't work. So we had to have some transition technologies. The first one is to tunnel. So if some people are already using IPv6, but the middle of the network isn't, so you just put the IPv6 packet in an IPv4 packet. The other side, you just take it out again. Well, basically, that part is done. You don't need that anymore. Then we have dual stack, where you run them next together. So you build up the IPv4. The IPv4 gets to 100%. You tear down the the IPv6. You build it up, gets to 100%. Tear down the IPv4. So let's have a look at how that works. So this is tunneling. So this is the idea behind dual stack. So you move from IPv4 only to both, and then just remove the IPv4, and then you are completely 100% IPv6. Well, there is one thing. So if you turn on IPv6, and basically what services like websites need to do is put an IPv6 address in the DNS. And then people who have IPv6 on their local network will try to connect to the service over IPv6. But what if there is something not going right in the middle? Then the IPv6 packet doesn't make it. And then you have to wait for timeout and retry over IPv4. Well, that takes a long time, so that is not good. So they came up with something called Happy Eyeballs. And eyeballs is the name we use in the internet industry for users who watch stuff on the internet. So you want these people to be happy. So that means no lengthy timeouts. So basically what they did, they made the browser such that they either send one request over one protocol, and the other comes really closely after, so you don't want to wait for a timeout, or even send them at the same time. And if one connects, they just cancel the other one. So basically, if only one protocol works, then it will automatically find the other one so fast that the user doesn't notice. So that is not a problem anymore. So where are we with this dual stack deployment? Well, we can still basically assume that everybody has IPv4. So we only look at how many people also have IPv6. And what you can see is that it basically started at almost 0 10 years ago to about a third now. This is worldwide. Of course, it's different per country. You see that in Germany, just went over 50%. Belgium is a bit higher still. And here in Holland, I have to admit that we are only just about half of that, so 27%. And some countries that are actually pretty pioneering in the internet world, like Sweden, they are doing it so well. So that's really weird. And also 2 countries that you think they are neighbors, so why aren't they so different, like Portugal and Spain? So that is strange. Okay, so that means that we were at basically 0 10 years ago, a third now, and we're progressing about roughly 5% per year down the slope here. But that's the fast part, right? So it's an S-curve. So it started slowly. It's also going to end slowly. So the last few old people who really don't want to get rid of their Windows XP machine that they have been keeping running for 20 years, nobody knows how. So this is the people you have to deal with when you reach 95%, and then everything is going to slow down. But even if we just assume 5% per year, it's going to take another 35 years, right? So this is not going to work either. So basically, either we have to stay on IPv4. Well, that doesn't make much sense. But there's actually technologies that can help. Like at home, we have multiple devices. We get one IP address from our ISP. We use the network address translation stuff in the cable modems or the ADSL modems or whatever. So what if the ISPs just do the same? They translate and share the address again. So now you're not sharing one IP address with your home. You're sharing it with all your neighbors in the entire block, or maybe even in the village. So these IPv4 addresses are going to get pretty busy. Or what we do, we give people IPv6, but then if they want to access something that is only reachable over IPv4, then the ISP translates your IPv6 packets into IPv4 packets. So how does that work? Well, the IPv6 system asks the DNS, hey, I want to go to Twitter. I think they are still IPv4 only. And then the DNS looks up IPv6 address for twitter.com, gets nothing. So then it creates a fake IPv6 address. So it takes the 32-bit IPv4 address and adds to that 96 bits that are routed towards the NAT64 translator. So then the IPv6 system gets back the address, sends the packet. The 96-bit prefix is routed to the NAT64 translator. So the packet gets there. NAT64 looks at the last 32 bits, translates the whole thing. Most of the fields, they are basically the same. So that's doable. Sends the packet to Twitter, gets an answer, translates it back, sends it to the user. And so the IPv6 clients can reach IPv6 services such as websites. Doesn't work the other way. You cannot make an IPv6 client reach an IPv4 client reach an IPv6 service because you cannot put a 128-bit IPv6 address into a 32-bit IPv4 address. That would be some really terrible shoehorning. So the good thing about NAT64 is that if you go to Facebook, which do have IPv6, that means you don't go through the NAT64. You only use the NAT64 for stuff that is only IPv4 only. So as more stuff goes to IPv6, the NAT64 translator has less work to do. So that is the great thing about NAT64. It has its own built-in exit strategy. Speaking of NAT, because we have so much address space in IPv6, there's never any reason to share one IPv6 address with multiple systems. So basically, we never wanted to do IPv6 to IPv6 NAT. So that's not something you can use in practice. Of course, you can always build a device that does that, but all the extra protocols that make it work, that work around the side effects, they don't exist in IPv6. So expect, if you implement this anyway, expect to see bad things happen. So this is comparing NAT64 to ISP NAT, and you see that there are some pros and cons to both, but in general, because NAT44 locks you into the IPv4 world, I think NAT64 has the advantage. Although, of course, I am slightly biased because I'm one of the authors of NAT64 specification. And there's one thing that NAT64 won't let you do. That is, if you have an IPv4 only application, then it's never going to ask for the IPv6 address of twitter.com. So how do we solve this? Well, Apple solves it one way. That is to say, well, if you want to have your application in iOS App Store, then you just have to support IPv6. So simple. Other OSs, they do this slightly differently, and they say, well, we add an extra layer, extra software layer, that if we have an IPv4 only application, which that doesn't make any sense, because IPv6 has been around for a decade before the phones. where even the IP capable smartphones came along. And this is mainly about the smartphones because it's the mobile networks who are now doing this. So this is especially important for mobile phones. They have to be behind Net64s. I mean, with like I said, the grandma with the Windows XP, that's all more complex. So the few ISPs are ready to put entire user bases on fixed networks behind Net64. Anyway, so I don't understand why there are still IPv4 only applications, but there are some. So what you do is you add an extra layer that intercepts the system calls that want to connect to IPv4 destinations, translate it to IPv6, send it to the Net64, translates it back to IPv4. So translate everything twice, that still works, right? So basically, this is a graphical representation of the end game for Net64, and I mean, I call this IPv4 as a service, because basically extra servers that you can put on top IPv6. And what you can see here, that if you watch a movie on Netflix, then if you are an IPv4 user, obviously you talk to Netflix in red over IPv4. If you're an IPv6 user, you talk to Netflix in blue in IPv6. But last year when I tried Disney Plus, they didn't have IPv6. So suppose that I had an IPv6 only system, then I would have to send my my packets to the big factory where they are changed over to IPv4. This, of course, seriously, this costs energy. I mean, if you data centers are using so much energy, it's insane. And then they're sent to Disney over IPv4. So this is inefficient, but the good thing is that, of course, the ISPs are going to say, well, I have a bunch of these translators, but you keep sending more Star Trek and Avengers and everything, and the traffic is growing like crazy, and I don't want to keep buying these things. I know I need a few. I mean, I cannot do IPv6 only right now, but if you want to send more traffic to my users, well, send it over IPv6, because I don't want to pay extra. Just the extra bandwidth is expensive enough. So Disney, get your act together and do IPv6. That is, I think, going to be the conversation these people are going to have. So that's the Net64 endgame. And I think basically nobody's going to care that some small stuff, some little website somewhere is going to be on IPv4 forever, because they need these big Net64s now. And then as more and more of the big stuff goes to IPv6 only, or sort of dual stack, then these Net64s are there. So the little stuff, nobody cares. So we're not going to reach the 100% anytime soon, but we are going to reach a very high percentage of the actual traffic on IPv6 in the next 5 to 10 years, I think. So basically, that's my IPv6 story.
Do you know whether, so the statistics you showed about the adoption of IPv6, I guess these are based on the number of connections Google sees, right?
Right.
It's not by volume, is it?
No, these are what they do is they put a little JavaScript thingy on some of their pages. So maybe 0.1% of their users, when they go to google.com, what they do is they give them something you can load over IPv4. They give them something you can only load over IPv6 and see what happens. And then, of course, the people who don't have IPv6 are not going to be able to load the second thing, and then they can record this.
Because it would be kind of interesting how much volume or share of the traffic volume is going over IPv6. That would be interesting.
Yeah. So one thing that's interesting is that the Amsterdam Internet Exchange, one of the 3 big internet exchanges here in Europe. Well, there's others, but the Frankfurt, Amsterdam, and London, they have the 3 biggest ones. So Amsterdam, I've been checking because they've had statistics for a long time where you can see how much of their traffic is IPv6. And for many years, it was basically 1 pixel on the graph. And now it's about 2%, I think. So it's still very little, but you have to realize that all the big ISPs are talking to the big content people over direct connections. So the internet exchanges are not representative for most of the traffic. But it's still strange that it's only so little, even though, it's so strange that in 2005, I published this book about IPv6. If you had told me then that we'd be at 33% today, 15 years later, that sucks. Because one story I've been telling people is, well, basically the transition from IPv4 to IPv6 is either going to be the biggest triumph of engineering ever, because we changed the whole internet and nobody realized, or it's going to be the biggest failure because we changed the whole internet and it didn't take. And we still didn't know which way it was going to go.
Right.
But what I realize now, the whole internet, that it was too ambitious, because 33% of today's internet is insanely large. That is like the internet from a couple of years ago, right? So huge amount of equipment, of devices, of traffic, but it's still only 1/3. But the thing is that if that third had also had to be on IPv4, then IPv4 wouldn't be able to cope with that.
Right.
So even though IPv6 didn't conquer the entire world just yet, it's probably not going to do that in the next few years, but it's still doing what it was designed to do, for which it was created, which is to take the pressure off of IPv4. So we had a way to keep growing, even though we were running out of IPv4 addresses. So in that sense, it is successful.
I'm sure it's going to pick up. I mean, there's no way around it. I'm sure people that operate a carrier grade NAT are sick of it.
Right.
I sincerely hope they are.
Yeah, but on the other hand, I mean, what I've often seen is that people, they just take more and more complexity on board to give them stuff that they want, while networks work the best if they are simple.
Right. That's definitely true. Well, Ilić, thank you very much. It was a very good talk, and I hope my students will appreciate this. But as I told you earlier, they actually, in the evaluation of the course, they ask for more IPv6 content, and now they have it. Right. And hopefully they watch it over IPv6.
Well, YouTube, are you going to publish it on YouTube?
Yes.
YouTube has IPv6, so that should work. So
at least one of the
50.09% of your students, if they are regular Germans, they should have IPv6. Right?
That's true.
So if they have any questions, I'll leave it up to you to see if they're interesting enough. But maybe we can do a short follow-up if there is interesting questions.
Yes, that's a good point. Let's do that. All right. Thank you very much.
My pleasure.